Now I am pleased to turn the webinar over to Ed Fenton, your IWCS moderator. Ed, please go ahead.
Thank you, Connie. Our IWCS webinar series event is hosted by the International Cable and Connectivity Symposium. I am Ed Fenton, a cable industry advisor working with the IWCS team. As Connie said, if you have questions, please use the Q&A box on the bottom right of your screen to post a question anonymously. We encourage you to submit your questions during the presentation so we can include them during the question and answer period. If you wish to contact the presenter or IWCS after the presentation, you will be given the contact points at the end of the webinar. Please note that IWCS does not distribute the presentation slides from either our conference sessions or these webinars. However, please feel free to contact the presenter directly, and they will respond individually to you. Today we welcome Patrick Dobbins, Director of Solutions Engineering for AFL in South Carolina, USA, who will be presenting his paper on correlation OTDR for accurate measurements of optical length of fiber optic cables under diverse environmental temperatures. Pat Dobbins is currently the Director of Solutions Engineering for AFL. He joined AFL in 1992 after 13 years as a network design engineer at a major telephone operating company and as the engineering manager of a fiber optic cable startup company acquired by AFL. He received his Bachelor of Science in Electrical Engineering from Georgia Southern University in 1980. He holds 6 U.S. patents in fiber optic technology and has published multiple papers and articles on fiber optic technology. Pat, we welcome you today to present at today's webinar series event.
Thank you, Ed. Just as a quick comment, the actual paper today is about splicing efficiency improvements for ultra-high density fiber optic cables. This is a kind of a carry-on from a previously published paper that we did in 2015. So what I'll be covering today is I'm going to do a brief introduction about the paper, so give a little bit of the background. I'll cover about a description about what ultra-high density fiber optic cables are, and I'll identify the cost elements in field splicing for ultra-high density fiber optic cable. And then we'll kind of go to the heart of the paper, which is really to focus on the areas where the improvements have been made since these cable technologies have been introduced. I'm going to compare some data to a paper that we published at IWCS in 2015, which kind of covered the total value propositions of ultra-high density fiber optic cables and the network savings cost. This paper will focus on just the improvements in mass fusion splicing and cable preparation and closure preparation. And then I'm going to compare some of the new data that we ran on the new study for 2018, and then finish with a conclusion and summary. And then at that point, we'll entertain questions. So the base of this paper is in mass fusion splicing improvements since the original paper was published on the 64th IWCS in 2015. We're going to compare the data from the original study in 2015 that focused on splicing processes, comparing mass fusion to ultra-high density fiber optic cables to traditional ribbons and traditional loose tube cables for the lower fiber count. We're going to investigate 3 specific areas of mass fusion splicing processes that consume time, which again lead to cost and money. We've identified improvements in new technologies that reduce the time in each one of those 3 areas. And then we're going to summarize the time savings in each area. And then finally, we're going to identify the specific percentages for time improvements for each process. So as the description of what is basically the ultra-high density fiber optic cable, is basically is a fiber optic cable that goes into a very high dense packing factor, as in the effective cross-sectional area of the cable has a very high fiber count. The cable in question that the study was done under is a product that we make called wrapping tube cable. Other people have similar cable technologies and have different descriptions for it. We offer this product at 144 fiber all the way to 3, 4, 5, 6 at the time when this paper was published. Today, we've actually released now a 6912 fiber cable. This uses a ribbon technology that's called a collapsible ribbon is the generic term. Our trademark specific product name is called spiderweb ribbon, and basically what it is a collapsible ribbon that folds into a very small packing factor. With that ribbon technology, you're able to make cables with very small diameters and much lower cable weight than traditional cables. We offer it in armored versions as well as in dielectric versions. It's a dry core or basically is a dry core cable technology, but still will pass the water penetration test for the IEC as well as the GR20. It has been optimized for the technician. The technology itself has been optimized for quick cable entry and cable prep, and that leads to, again, some time savings in itself. And the mass fusion splicing efficiency has been improved significantly since the product was introduced in 2015. Overall, the cable technology as a whole offers a significant total cost. And if you go back to the original paper that was published in 2015, we identified basically 10 areas of cost savings, so you can refer back to that. This is what the cross-sectional diagram looks like for a PSP or polysteel poly double jacket single armored version. You can see at the very center it's somewhat of a unitube type design. It has longitudinal strength members that are embedded into the inner jacket. And then there's, of course, rip cords under both jackets. Under the inner jacket, there's actually a very slight rib that is a rip cord locator so that you can always know where your rip cord's at to facilitate improvements in time doing mid-cable access. Give me 1 second here. This, again, is just showing an 864 wrapping tube cable and what the cross-sectional diagram looks like. So the collapsible ribbon itself, as you can see where it would get the name spiderweb, it looks somewhat like a spiderweb where the individual 12 fibers are intermittently bonded to each other. And what this allows for is that the ribbon will literally roll up and fold and collapse. The identification on the ribbon uses a band marking or what we call strike ring marking with a base 5 numbering system. This is showing you 1 through 5 where you have individual bands to identify that are short bands for 1 through 4, and then 5 is a long band, and then progressively working forward you have combinations of long and shorts that take you all the way to the 12th ribbon for your counts below 3,456 fiber cables, and then there's actually 24 ribbons now designated as you go up to 6912. One of the other advantages with this spiderweb ribbon technology is that it can be de-ribbonized to do individual fusion splicing, which is very helpful in facilitating where you have just a few fibers being accessed and doing a mid-cable access technology. So the areas of cost impact for mass fusion splicing process that we focused on and looked at was basically cable preparation, the closure preparation, and the mass fusion splicing process itself. So in cable preparation, your individual steps are you do the prepared cable length, you do the ring cut, you open up and access the rip cords themselves, which allow you to remove the jackets, you do the sheath removal, then you go to the individual binder groups and you do the binder removals if necessary, and then if you had any type of water blocking tapes or yarns, etc., that block the intrices, you'll go through the process of removing those. All those are basic steps of the cable preparation. In closure preparation, you have the anchoring of the cable into the closure base itself and the sealing process, then storing the cable core or ribbon bundles themselves in the organizer and storage area, and then making transitions to the splicing tray, and then anchoring those binder groups to the splicer tray and the tray setup itself as far as coiling the binder groups or ribbons in the individual trays. The steps in the mass fusion splice process is, again, you get your length measurement by pre-routing the fibers in the tray. and going up to where your splice sleeve holder is at. You basically have to insert all your splice protector sleeves. You do your stripping of the coatings. You do the fiber cleaning. You do the cleaving. Periodically, you're going to have to do blade rotations, especially when you deal with ultra-high density cables, because you've got a certain number of cleaves allowed for the blade position. And you'll need to rotate the blade in order to keep the blade sharp. So typically, for example, with our cleaver system at around 83, 84 splice preparations, you're going to need to rotate a blade. So that's a time-consuming element. Then you have the mass fusion step itself, which is probably the fastest and easiest part of it. And then the splice sleeve curing in the thermal curing device. And then again, the last step would be, of course, putting that particular sleeve away. So improvements in cable preparation, just starting there, is some of the things we've done to improve and speed that process up is gone to a new ripcord. The ripcords are actually two ripcords, one on each side. We also have a rib that's on the top of the inner jacket, so as I mentioned before, that you can use for the basis of finding the ripcord for mid-cable access. We have a developed shaving tool that does the shaving of the jacket and takes you down to the ripcord, and then you can slip screwdriver under that ripcord and literally rip both sides of the cable jacket. This is can be facilitated either for an in-cable prep or mid-cable entry. Again, depending upon the type of network, you may need to periodically do mid-cable entry where you're not doing splicing of all the ribbons in the cable, but you're only accessing either one ribbon or a couple of fibers in that particular ribbon at an access point. Some of the other things that we've done to improve the cable preparation efficiency is that the binder itself, rather than being helically wound around the binder group, is actually edge bonded and back and forth, so I can literally slip the binder out of the way, access an individual ribbon, cut it, and then slip the binder back into place. And I'm not having to helically unwrap the binders each time. Again, a couple new tools, ring cutting tools and shaving tools have been developed since 2015 that have also improved the cable preparation process. We moved on and went to the closures. Well, a number of new closures are being developed. Some of those deal with the means of routing the binder groups. They have routing channels on them that actually provide physical protection, so you're not having to put binder groups into routing tubes and those types of things. They have an express area for storage. They also have protective pads that are used to anchor the binder group to the splice tray. And then transitioning from the organizer area itself, it has basically a protected zone that you transition with the spiderweb ribbon binder groups to the splice tray that's fully protected against the, on the opposite end of the cable entry area. So you don't have, your tray access is not competing with real estate where your cable entry point is near the closure sealing area. And then the last step I talked about a little bit is that these new foam pads basically give you a means of anchoring the binder group to the tray without putting a macro bend on the individual fibers. It basically is a split foam pad that seals around the binder group that you attach directly to the splice tray and does the anchoring there. That's also an element that speeds up the process. Just kind of looking at some photographs, this shows you how you route the spiderweb ribbon binder groups to the tray, and then how you store those in their individual channels that keep them protected. And then again, you see in the bottom middle series how the trays actually cross over, or the binder group crosses over and enters into the tray, and that the ribbons are effectively protected all the way from the cable entry point through the organizer, through the routing guides, all the way up into the tray itself. This greatly speeds up closure preparation time in that you're not having to furcate tube or spiral wrap or other elements to try to physically protect the fibers. the closure itself, organizer, is designed to do that, just like a splice tray protects the fibers in the splicing area. Some other improvements that have been probably the most significant improvements is in the fusion splicing equipment itself. The fiber holders, rather than the traditional holders that were basically had a spring-loaded clip or magnetized clip on the top, we went to what are called grooved or scalloped, that hold the individual fibers of the spiderweb ribbon array at a very precise alignment and a very precise spacing that the fusion splicer is looking for. This speeds up the process, reduces the number of errors that you would have, so you get a better alignment and you get a much more consistent yield. In the normal mass fusion splicing process, you typically will have, a ribbon failure of alignment in one in about 12 or 13 ribbons that you do. And what we're finding is that with this alignment new fiber holder, those numbers go down dramatically. One of the biggest area of improvement has been the thermal stripper for the ribbon itself that removes the coating off the 250 micron fibers and brings them all down to 125. We now have a thermal stripper that's outboard and not having to be attached with an umbilical, so it's rechargeable, battery operated, and it has an 8-second cycle time between heating. Previous thermal strippers would have been up in the 30 and 40-second cycle times. So it's very efficient, it's independent, you're not tethered to the machine itself, so you can operate away from the machine. And again, the 8-second cycle time is a very significant improvement. If you think about the number of ribbons that you may be doing, and you're doing, say, for 1728, you have 144 ribbons where you're preparing 288 ribbons for 144 of those splices. Okay, well, if you're saving 30 seconds on each cycle time, that's a significant time savings. Some other areas that have improved is the release of the CT50 cleaver, which is a Bluetooth-enabled cleaver. It has the ability to keep count independent of your fusion splicer. Used to use your arc counts to keep count of where your cleaver had been used, and that would tell you when to do your rotation of your blade when you'd reach the point that you were starting to dull the blade. Well, now the cleaver keeps count and notifies the fusion splicer that it's reaching, that it's counting it's time to rotate the blade, and literally it can be set so that the blade rotates automatically when it reaches that point, depending upon the settings that you want to set on the cleaver. And then some other improvements have been in the mass fusion splicer itself. Offset errors, it now has the ability to automatically try to handle the offset errors that might be taking place when you go put both the fiber holders in. You may have one fiber that has a little bit wider gap than the other fibers. Well, the old method used to be that you take your finger and would tap the fiber holders, trying to jostle it into position. Well, now the machine senses that and automatically does that. An example of which is in the next video. Oh, I'm sorry, in one of the following videos that we'll show. This is just showing you some close-up details of the fiber holders itself with the scalloped ends. You also see the arc gap area where the Kyotos are located. The new RSO3 thermal stripper that has the 8-second cycle time, and then the CT50 Bluetooth-enabled cleaver. Again, all these refinements took place after the wrapping tube cable had been introduced with spiderweb ribbon, and there was things that were done to continue to optimize the splicing process and reduce splicing time. So an example of the video, how the offset errors are corrected, is in the following little video clip. The alignment has started. It's noticing a offset error on one of the fibers are off a little bit. So it's snapping the wind protector open and close, which basically bounces the fibers so that they reposition, take care of the offset error, and then continue the process. And it does this all automatically. And of course, you couldn't see the results, but they were showing basically all the splices were now in spec. So to get to the heart of the paper, what we did is we redid the splicing study. And this is showing the original splicing time that were measured in 2015, and this broke it into cable prep, splicing time, and then total time. We did, pardon me, comparisons of traditional loose tube, 144 fiber, which is single fiber, comparing to 144 fiber wrapping tube. Then we moved into 288 fiber standard ribbon versus 288 wrapping tube cable. Then we went to 432, and again against traditional ribbon versus wrapping tube. And then we went to 864. At that time, the 1728 fiber had just been introduced and was not included in the original studies. So what you can see is this is in the past, in 2015, we were probably in the neighborhood of around a 30% average improvement over splicing time of either loose tube, actually loose tube was more like about 50%, but against traditional ribbon was about a 30% savings in time. In 2018, we went and did measurements on wrapping tube. This time we did it all the way up through 1728, again showing the cable prep time, the splicing time, and then the total time. And you can see that starting at 144, you're a little over an hour and 12 minutes. At 288, about total time was in somewhere in the neighborhood of about an hour and an hour and 40 minutes. And then 2 hours and 24 minutes on the 432. 864 total time was a little over 3 hours and 36 minutes. And then the 1728 was right at 7 hours to do. So when we compare that data to the new data, wrapping tube to wrapping tube, in other words, the time spent doing wrapping tube in 2015 versus wrapping tube that was done in the 2018 study, you can see 144 through 1728. Now, we took the 1728 data for the 2015 and had to extrapolate it because we did not have the data at that time because it was not included in the study. And what I did was took the 864 information and doubled it of just the splicing time. I only counted cable prep time one time. And this shows you in the slide basically is a comparison of the percentage change by fiber count, where we ran from 29.7% improvement on the 144 to 39.8% improvement on the 1728, again comparing to extrapolated data. And overall average of average was 36.8 improvement, which is a pretty significant number when you look at the cost of splicing. This is showing, comparing the 2018 data on the wrapping tube compared to the 2015 loose tube and traditional ribbon data. Again, a little bit unfair in a comparison because, again, the improvements in a lot of the equipment and the splicing processes. But the key part of the data is that it shows about 144 was a 63% improvement from 2015 of traditional loose tube, up through 288, 33.5, 432 was 42.2, again 864, 48.4, and then 1728 data being compared was 52.9. So the total improvement from traditional ribbons, traditional loose tube, was an average of about 49, almost 50% improvement from the 2015 data. So when you kind of summarize, this is the introduction of ultra-high density fiber optic cables with class 4 ribbons some years ago presented a paradigm shift in technology. Benefits on fiber counts, higher fiber counts, higher density. 10 years ago, I wouldn't have believed that people were looking at meeting an application for fiber counts in the 6912 fibers. and today it's pretty commonplace, especially with the point-to-point on the data centers. So we fully exploited this technology to requires a synergistic approach, which is basically looking at the three areas of time savings. We continue to try to refine not just the cable preparation, but the closure systems and the mass fusion splicing systems for a full improvement of an integrated solution. In summary, the splicing data that was compared to the original 2015 study to the 2018, we averaged 49.9% improvement over traditional designs, and then a 36.8 improvement over wrapping tube to wrapping tube improvements from 2015 to 2018. The system's approach to splicing time improvements has had a significant impact on total system cost for the ultra-high fiber density networks. And I'll tell you is that we've got a lot of reported field data that is even showing improvements since then. We've had a couple of reports of people doing 17/28s that they're completing rather than the time study that we show at 7 hours are in the neighborhood of 5.5 hours, which basically if you do it, it's an average of about a 2-minute cycle time per ribbon. The equipment itself is capable of about a 1-minute cycle time, but you have fatigue and you also have, elements of just the process itself that leads to just a little bit of inefficiency. But again, getting down to a 2-minute cycle time has been pretty significant. And with that, I'll close.
And thank you very much, Pat. At this time, we will ask as many questions from the attendees as time permits. We'll start with this first question. Are there any guidelines on the peel back distances using rip cords? And then the second part of the question, is there a minimum or a maximum recommendation for optimal splicing or termination?
Okay, the first question was what's the cable prep length guidelines? It's really dependent upon the closures themselves and whether or not you're doing an in-splice or you're doing a mid-cable access. I'll tell you that typically on in-preps, we're prepping around 96 inches. Mid-cable access, I'll take that back. In-preps is about 120 inches. Mid-cable accesses typically are about 96 inches. And what was the second part of the question, Ed?
Glad to repeat. Is there a minimum or a maximum recommendation for optimal splicing or termination?
Yeah, there's a number of standards out there. The mass fusion standard that most people refer to is looking at a .10, but it's also done on a percentile of total number of splices, so you're allowed some deviations above or below. Most people write their own specs and reference that number, and then the deviation becomes a company standard that's defined in their splicing specs. So in other words, they'll say that 90% of them have to be at that number, and then they may say that the blue fiber of the ribbon must average at the length of each splice point of a number.
Great, thank you. Next question. Is there any data to show improvements in assembly attenuation using the new mass fusion splicing techniques?
Yes, there is some published data out there. Fujikura did some splicing analysis that have been done on some different fiber types. That's data that we can potentially share.
Okay, great. Next question. Can these new splicing preparation techniques also apply to the full spectrum of optical fiber cable designs beyond ultra-high design cables, or would this be overkill?
No, they can be applied. For example, your traditional ribbon will see improvements with the new hot jacket stripper technology. The scalloping won't, the fiber holders doesn't really help you one way or the other than just aligning 4 collapsible ribbon fibers. A traditional ribbon cable could still use that same fiber holder and not have an impact. So when we get into hybrid situations where we're splicing SWR to a traditional ribbon, we'll use the same fiber holders.
Okay, great. Thank you. Next, do you have a procedure to clean the machines to assure accuracy, or is that not a concern?
Yes, we do. There's actually a kit that's been developed called a V-Groove cleaning kit. That if you look on our website, aflglobal.com, and you look in the accessories in the splicing area, you'll find a V-Groove cleaning kit, and there is a set of instructions as well as an animated video that shows the process of how to properly clean a mass fusion splicer and clean the Kyoto and everything else in the general region of the splicing area in the fusion splicer.
Okay, thank you. Next, what is maximum fiber offset with the automatic alignment feature?
It can be set variably, but it's in the neighborhood of around 50 microns.
Okay, thank you. I am looking at one last question. We are done with questions. So Pat, what I would like to do is thank you very much for presenting this very interesting and important topic today. Please note the contact points being shown should you wish to contact Pat after today's event. Each of these IWCS webinar series presentation events are recorded and will be archived on the IWCS.org website. It normally takes up to 2 weeks for these to be posted. The IWCS webinar series will conduct presentation events on a monthly basis. Webinar events will take place on the third Friday of each month at 10:30 a.m. Eastern USA time. Our next scheduled webinar event will be on Friday, June 21st at 10:30 a.m. Eastern USA time. Each of you will be receiving an announcement for the event of a few weeks prior. Please feel free to share our announcements with your colleagues so that they can join in and register as well. For over 67 years, the IWCS International Cable and Connectivity Symposium has been the recognized leader showcasing new technologies in cable and connectivity products, processes, and applications. Our next annual international conference will take place on Sunday, September 29th through Wednesday, October 2nd, 2019, at the Charlotte Convention Center in Charlotte, North Carolina, USA. In addition, the third annual UL and IWCS China Cable Connectivity Symposium will take place on Tuesday, March 17th through Thursday, March 19th in 2020 at the Marriott Hotel City Center in Shanghai, China. Please visit our website for more details. In just a moment, you will see a brief survey so that you can provide us your feedback and comments on today's event so that we can further improve this webinar series for you. Thank you for participating, and this concludes today's event.